So the goal of this experiment is for us to determine, of course, if the reaction is spontaneous or not. And don't forget, of course, if our reaction is spontaneous, that, of course, indicates that delta G for this reaction, of course, is going to be less than 0. Honestly, that just means, of course, that the value will be negative. So how are we going to determine, of course, these thermodynamic quantities? Well, there are several, of course, thermodynamic quantities. The first, of course, right, is delta G. Determine if the reaction is spontaneous or not. Our next thermodynamic quantity, of course, is enthalpy, which is, of course, delta H. So we're also going to be determining delta H of this process. Remember, of course, that delta H, of course, is just a change in enthalpy. If delta H, of course, is negative, that is going to indicate, of course, that our process, of course, is exothermic. If delta H is positive, of course, at the end of this experiment, it would mean that the reaction, of course, is endothermic. And our third, of course, thermodynamic quantity, of course, is entropy. Entropy, of course, is just a measure of the disorder, right, of the system. As we noted, of course, in class, when the system is becoming more chaotic, that means, of course, if you're taking a solid and it's being converted, of course, to a gas, then that system is becoming more disordered. The more disordered that system is, right, then delta S, that, of course, thermodynamic quantity, is equal to, of course, a positive value. So when you do your calculations, if the reaction is becoming more disordered, then you would expect, of course, that the value of delta S that you obtain should be positive. If the reaction is becoming more ordered, so for example, if water condenses, right, from that gaseous state to that liquid state becoming more, of course, ordered, then delta S, of course, will be negative. So our goal, of course, at the end of this experiment is honestly to determine, of course, right, all possible thermodynamic quantities, of course, for the dissolution. So we're going to look, of course, at the solubility of potassium nitrate in water. All right, so now please note, so most solids, including, of course, potassium nitrate, will dissolve in water. And when they dissolve, of course, in water, what happens, of course, is that we generate, of course, an equilibrium process where we produce, well, the potassium ions and, of course, the nitrate. So when your solid, of course, dissolves in water, typically, of course, the potassium nitrate, we know for sure that our potassium nitrate, of course, solid, will, of course, what, ionize completely. Oh, beautiful. That's a wonderful equation. That it will ionize, right, completely. However, when we get to a point where we do, of course, as our saturation point, when the solution is completely saturated, then you should note, of course, that, of course, we have what? There will always be some undissolved solid that's in equilibrium with, of course, what? With, of course, our aqueous ions. And so under those conditions, an equilibrium, therefore, will be established. Now, some, of course, salts is going to almost completely dissolve in water, like potassium, of course, nitrate, and therefore the equilibrium constants under those circumstances will be much larger. Other solids, of course, are actually sparingly soluble, right? And therefore, when you calculate the equilibrium constant value, then, of course, those values will be much smaller. And so because an equilibrium is established, we know that we should be able to calculate what? Some equilibrium constant. So how do we express this? Well, because we're looking at the solubility, of course, of this compound, the equilibrium constant is not referred to as Kc, it is not referred to as Ka. The equilibrium constant value is referred to, of course, as Ksp. It's called the equilibrium solubility product constant. And like all, of course, equilibrium constant values, you should note there's an expression for this. It's going to be, well, the concentration of our products divided by, right, the concentration of our reactants. But what do we note? Do you agree that, of course, what, solids and pure liquids do not appear in the expression? And so because they do not appear in the expression, the equilibrium constant, right, the solubility product constant value, is just the concentration of those species. So the first thing we're going to do today is to calculate, of course, the equilibrium constant value. So why is that so important? So please therefore note, so I'm going to take a few minutes and just remove all of this information. Please note that the equilibrium constant value is actually, of course, related, right, to delta G. Remember we said that when delta G is less than 0, our process is spontaneous. Likewise, when we covered our section on equilibrium, we also, of course, recognize that K equilibrium, if it's greater than 1, then our reaction what? Then our reaction favors our products. So there is, of course, an equation that actually relates K equilibrium to delta G. And that equation states what? That a change, of course, that gives free energy is actually equal to minus RT natural log of K. Now that K value, well, it could be, of course, Ka if I was dealing with a weak acid. It could be Kb. In this case, of course, it's equal to what? Ksp. Now, T is our temperature. Please note, temperature must be in Kelvin. But what about R? So R is our gas constant. But if you recall when we looked at the ideal gas equation, PV was equal to what? nRT. Under those circumstances, right, please note the units for R and the value was 0.08206. In terms of units, it was liters, atmospheres, mole to the -1, K to the -1. Do you think it's the same, of course, value in the units? Absolutely not. Because delta G, like delta H, right, they're in units of what? They're oftentimes, of course, in units of kilojoules or in joules. And so, in this equation, please note, R is still the gas constant, but now its units, right, is also now going to be in what? Joules. And it's equal to 8.314 joules per Kelvin per mole. So please note as you complete these calculations, the value, of course, for R. Alrighty, don't forget our goal. What was the goal? We're trying to determine what? Delta G, delta H, and delta S. So how are we going to get there? Well, in the experiment, we will know the temperature of our reactions, and you'll see that we can also calculate what? Ksp. How can we calculate Ksp? Well, I hope you recognize that the potassium ion concentration is directly equal to what? The nitrate ion concentration. These are just concentration terms, and so the potassium ion concentration will just be what? Will just be the moles, right, of your potassium ions over your volume in liters. And so in this experiment, we're starting off, of course, with what? With approximately 20 grams, this is approximately, of potassium nitrate. So do you agree? We should be able to calculate what? The moles of potassium nitrate, which is also the moles of our potassium ions. If you know the moles and the volume in which the first crystal appears, right, then you can calculate the molarity for each. The product of the molarity will give us, of course, what? Ksp. Okay. So we know, of course, the natural, right? We know, of course, Ksp. We know the temperature in Kelvin. We have the value of R. We can readily calculate, of course, delta G. So what about the other thermodynamic quantities? Well, to do so, we're going to look at an expression. Please keep in mind that we also noted in class that delta G was equal to what? Was equal to delta H minus T delta S. So that's an equation that we discussed, where if delta G, of course, is less than 0, our process, of course, is spontaneous. That always happens under certain circumstances. Delta G is always less than 0 when your reaction is exothermic, when that is negative. Always, of course, when it's spontaneous. And we looked at different scenarios, right, in lecture. So how are we going to use this now, of course, to determine delta H and delta S? So please note, we're going to combine, of course, equation 1 with equation 2. And so when I do that, what do I have? Well, minus RT, natural log of K SP is equal to delta H minus T delta S. So I'm going to rearrange my expression. So natural log, of course, of KSP is going to be equal to, of course, delta H. So I'm literally dividing this equation through by minus RT. So take a note of this. So it's going to be minus, of course, delta H over RT minus, of course, delta S over R. And I lied about that, it's plus. So again, for those of you for mathematics' sake, keep in mind I'm dividing through by RT. All right, so therefore, this term becomes minus delta H over RT, so I'm dividing through by RT. Now, this is a negative sign here. If I divide through by negative RT, then T cancels. That's no positive sign, delta S over R. So I need for you to recognize that this somewhat looks, of course, like a linear relationship. Remember mathematics, right? For a straight line graph, y is equal to what? Mx plus b. And so in today's experiment, you're going to be plotting a graph of the natural log of Ksp versus, of course, 1 over temperature. Don't forget that this temperature is the temperature at which we're going to observe the first crystals, and that unit of temperature must be in Kelvin. When you plot this graph, you're actually going to obtain, of course, a negative value for your slope. Okay. So I'm going to take my equation now and make it look somewhat, of course, in this form. So you should recognize that my y-axis is what? The natural log of Ksp is equal to m. So what is my slope? My slope, therefore, is going to be what? Negative delta H over R. What is my x value? It's 1 over temperature. Why? Because what am I plotting? I'm plotting, of course, the natural log of Ksp, my y-axis, over 1 over temperature. That's my x-axis. And then my intercept, B, will be, of course, delta S over R. Now, the beautiful thing about this is, if you plot your graph in Excel, do you agree? In Excel, you will know the value for that slope. You'll take that value, therefore, you know R, so you'll calculate delta H. And then you can do the same, right, of course, for delta S. So please note, as I go through today's experiment, you will know the exact mass of potassium nitrate that we're starting with. You'll know the volume each time, of course, we form that crystal. And so you will be able to calculate the potassium nitrate concentration each step along the way. Remember, your equilibrium constants, right, are all temperature dependent. So as we change that temperature, right, Ksp will change, the temperature will change, and so when you plot that graph, based, of course, on that equation for that line, you can calculate the slope. You can also solve for the intercept. So in this experiment, right, what I have here in my test tube is 20.126 grams. So you want to record that number, right? So we have 20.126 grams of potassium nitrate. And then to that, of course, I've measured out, of course, 15 mLs of water. So we're going to be adding, of course, the water to the solid. And then I'm going to mix for a while. And then we're going to increase this temperature, right, until we get to the point, of course, when the potassium nitrate completely dissolves. Under that condition, of course, I'm going to have a saturated solution. But if it completely dissolves, right, then that's really not an equilibrium system because there's no what? There's no, of course, undissolved, of course, solid. And so I'm going to cool this down once it's completely dissolved, and then I'm going to be recording the first temperature, right? I'm going to be recording the temperature at which the first crystals appear. That temperature will be the temperature that we're going to be using, of course, right, as we try to plot our graph for 1 over T. But don't forget that as I give you these temperature values, the temperature is going to be in degrees Celsius. You'll need to convert that, right, to Kelvin. Alrighty. So I'm going to go ahead. I'm going to start heating warming the solution. I'm actually going to lower the test tube in this water bath. And we'll also need our thermometer to be immersed later. And then I'm going to go ahead, right, and just lower the thermometer into the solution. Okay. I'm just going to remove that thermometer for a while. Because honestly, I just need to know the temperature at which this solution, at which the crystals first appear. So the goal here is to determine the temperature at which we first observe the crystals. At that temperature, of course, the solution is said to be saturated, where we have, of course, an equilibrium established, where we have our undissolved, of course, potassium nitrate, of course, in solution with our potassium ions and nitrate ions. So I'm just waiting to record the temperature at which we observe the crystals. And then after that, I'm going to go ahead and also record the volume of the solution. Because remember now, we need to calculate the molarity. We have the mass of potassium nitrate. We can solve for the moles, but we also need to know what the volume. And so the volume that is important is the volume, right, under which, of course, equilibrium is established. And how am I going to do that? Well, I'm going to remove, of course, these devices. And then I will, using, of course, a separate, of course, test tube of equal size and hopefully equal volume, right? I will literally, of course, just mark off exactly, right? I'm going to line it up later and then determine, of course, the volume just based, of course, on unfortunately, just inspection. So the temperature at which you observed the first crystals was at 74.5 degrees Celsius. And don't forget, you need to convert that, right, to Kelvin. So how am I going to go ahead and determine the volume? So I'm going to roll this around so that you can all see this. I'm going to remove, but not completely, because I don't want to, of course, lose any of my drops. Well, now you can see a lot of crystals are forming. And I'm going to add, of course, water to this container. So I'm going to be adding water directly to this container. Alrighty, so now you'll see that I've lined up both containers. And so the volumes, of course, are more or less all identical. But again, this is just an approximation, unfortunately. So when you look at your sources of error, this is a wonderful possible, right, source of error. And so I'm going to transfer this, the water now to my graduated cylinder, and I'll be able to determine the exact volume, right, of this solution. In the meantime, I'm going to go ahead and return it, of course, to my water bath. And the challenge here is to make sure that I continue heating after I've added, 5 mLs of water to this. So I'm going to be using 5 mLs of distilled water. So I'm going to add an additional 5 mLs of water to the container. And to determine, of course, the new volume and the new temperature once the first crystals appear later. Alrighty, so again, we're going to wait for the first sign of crystals. We'll record the temperature, and in addition to that, of course, we'll also determine the new volume of our solution. And so again, in the second part of the experiment, right after we added, of course, additional 5 mLs of water, the temperature at which the first crystal appeared was 60.2 degrees Celsius. And so what I'm going to be doing now is that I'm going to send you the remaining data for our 6 trials. So please just use the data that is provided on the data sheets once submitted. Thank you.